Hello, everybody. Thanks for being with us this afternoon. I hope you have had a wonderful first day of the summit. My name is Mahdi. I am here in my capacity as a founder of an ML machine learning consultancy company called MLBoost. And what I will be talking about is uncertainty quantification using a class of methods called conformal predictors and how these methods can increase the reliability of any ML model or any ML application. So the material that I will be presenting here is highly inspired and sometimes just directly borrowed from my company's YouTube channel, MLBoost. The difference is that here I will try to make the slides, the content that I present for this session, as high level as possible. That means that we try not to dig too deep. For example, we are not going to talk about how some of the very important equations behind conformal predictors are derived. But obviously, of course, you are more than, if you are interested to really get an in-depth understanding after this session, you are, of course, more than welcome to visit a playlist on the channel that is specifically for conformal predictors. And if you have any questions, again, you are more than welcome to reach out to me after the event. But overall, the objective of today's session is to make sure that at the end of this 1 hour and a half, you guys will be equipped with a foundational knowledge that is solid enough for you to determine for yourself if and how conformal predictors can help you, what they can offer to you in whatever ML application that you are working on. Typically in workshops like this, I focus a lot on going through implementations, showing code and Jupyter notebooks and the like. But for this particular audience, I was not really sure how many of attendees would already have some level of familiarity with uncertainty quantification or especially conformal predictors. So I wasn't really sure how useful just focusing too much on Jupyter notebooks can be. Because of that, what you will see is will be a mix of different things. I will start by a motivating example that I hope will be relatable to a lot of the audience here. And yes, it's going to be in the context of LLMs. And then after that example, we will take a few steps back to review some of the very, very, very foundational concepts that underpin basically all conformal predictors. So this part of the presentation, this second part, will be a little technical, but I think we can go over it. And then after that, I will point you guys to some advanced applications that range from forecasting to conformalized retrieval augmented generation. And then after that, I have some Jupyter notebooks that show code implementation of conformal predictors. I will go through the code, show you what's going on, and those notebooks will cover both classification examples and regression. So again, I said that the objective here is to make sure that you guys are well equipped by knowledge that is solid enough for you to determine for yourself what conformal predictors can offer to you. For that to happen, obviously, you guys need to ask questions. And I'm really hoping that we can keep this session as engaging and as interactive as possible. So feel free to ask questions in the middle of the presentation whenever something is not clear or whenever you would like me to repeat something. And I think you can, so we talked that you cannot unmute yourself, so you have the option of typing your questions in the chat and I will make sure to keep an eye there. And so whenever any question comes up, I will answer it. So, Shab, please ask questions. So, but what is uncertainty quantification? Why do we care about it? Why is it important? So, if you think of almost any ML use case, making predictions are such an integral part of it. Predictions can be like forecasting something in the future. It can be also predicting the next token in the context of LLMs. So predictions are everywhere. And then we use models for this. But the truth is that our models are far away from being perfect, whether we admit it or not. There's always some level of uncertainty in the predictions that any model makes. So we have given the presence of that imperfection, we have two choices. We can either pretend uncertainty is not there and just go our way. Some people may buy it, a lot of people will not. And then the other thing we can do is just acknowledge the presence of uncertainty and do our best to provide a picture that is clear enough with respect to the level of uncertainty. In other words, we can acknowledge the presence of uncertainty and try to measure it. When we do that, the users of our models, decision maker, or anybody who is going to rely on the predictions that we make, then they can decide for themselves how much trust they want to put in the predictions. This will depend on a lot of things. For example, how comfortable the person is, the user is with risk, or how high stakes the application is. And I hope so. I think our job as model developers is to paint that picture of uncertainty, try to quantify. And I hope we can all agree that acknowledging the presence of uncertainty and trying to quantify it is just much, much better than simply pretending that uncertainty does not exist. So let's kick things off by an example that I believe will be relatable to a lot of attendees here, showing what conformal predictors have to offer to LLMs. So LLMs with conformal predictors. This is and what I'm about to show is an ongoing work that one of my mentees, Bhargava, has been working on, and he is also attending this event. So please make sure to reach out to him if you want to know more about the work that I am about to present in this part of the session. The work is under the umbrella term of efficient conformalized sequence modeling. Efficient conformalized sequence modeling. Natural language is a specific type of sequence. And then here, I want to, hold on a second. Yeah, I want to, hold on a second. Yep, better. So here I want to present, you need to go in the back, put this on the road. So I am about to introduce a tool that we have developed that we call conformalized. Sorry, I don't like what this is doing here. 1 second. I'll play an animation. Oops. Something wrong. I can let's see. Yeah, okay. So, yeah, sorry about that. So, yes, so I was telling that the work that I'm about to present is under the umbrella term of efficient conformalized sequence modeling. Natural language is a specific type of sequence. And I want to talk about a tool we have developed that we call LLM Religar. You can think of it as a reliability layer that can be added on top of any LLM to make its outputs trustworthy. Again, a reliability layer that can be added on top of any LLM to make its outputs trustworthy. Obviously, reliability is a subjective matter, and when it comes to LLMs, there are at least two very important components that any reliable LLM application should satisfy. The first one is, as I mentioned before, is quantifying the uncertainty of the LLM's outputs so that we can give the user a sense of confidence in the outputs. Once we do that, then the users can decide for themselves how much they want to trust the outputs of the LLM or don't trust. And then our tool, Religard, makes that uncertainty quantification happen by outputting a set of answers rather than just a single answer. Again, outputting a set of answers, a collection of answers, rather than just simply one answer. And then once we output that set, obviously the shorter that set, the more confident a user can be in the outputs. For example, if the set that is outputted has only one answer, one element, then that is a sign that our model is very confident in what it has outputted. If instead of one element, the set has like 10 elements, that is a sign that we cannot really trust any of the single outputs. We have 10 different outputs. It's just difficult. It would be just difficult to pick one out of the 10. So the shorter the set, the more confident the user can be in the outputs. In other words, the length of the output set is a proxy for uncertainty. Now, let's say we output this set. The next question is that are there any guarantees that this set will include the correct answer? Because otherwise, if there are no guarantees, then it's just difficult to see how outputting multiple answers is beneficial. So are there any guarantees that the output set will include the correct answer? And the answer is yes. The answer is yes. There are what's called statistical guarantees. What do I mean by statistical guarantees? It means that when we output these sets, when our tool Religard, when it outputs a set instead of one element, then the probability that the output will not contain a correct answer, the probability that the set will not contain a correct answer is guaranteed to be less than a user-specified threshold. So when I say statistical guarantees, what I mean is that the guarantees are in a probabilistic sense. What that means is that there is never 100% guarantee. So it's always probabilistic. And then this threshold that determines the probability of the output not containing the correct answer is something that the user can specify. For example, if a user is just not very comfortable with risks, then they can decrease that threshold. If they want to make risks, then they can increase it. and the tool will adapt itself to the user's needs. So, and then linking that threshold to the length of the output set, the lower that threshold, the lower the user's risk tolerance, then our tool, ReadyGuard, will include more and more answers, such that to make sure that the probability that one of these answers is a correct one is above a threshold that the user is comfortable. This is how our tool, ReadyGuard, adapts to users' needs. It inputs a risk threshold from the user and then outputs a set whose length is such that the user requirement is satisfied. And now I talked about this, that this is a tool that uses conformal predictors. You can think of it as a reliability layer that can be added to any LLM output. What it does is that instead of outputting only one answer, instead of making only one output, it outputs a set of answers. And the nice thing about these sets is that there is always, they have a statistical guarantees, meaning that the probability that the set will not contain a correct answer is lower than a user-specified threshold. Now I want to show these, what we just discussed, in action. Let's say that let's start with inputting to our tool a question that is relatively simple, and let's also pick a relatively moderate level of threshold. Remember, I talked about the user being allowed to insert their own risk tolerance. So let's see that. What we are going to do is that, I hope you can see that screen here, but what we are doing here is that this bar, that you see, it determines the user's tolerance for error, where error means that the output set does not contain a correct answer. Then we move it to the right, that means that we are increasing the risk tolerance, user's tolerance for error. Right now it's about 0.5, a relatively moderate value. And then with that threshold inputted by the user, then the user will ask a question. Can you guys see the question here? I think it's a little too small, is it not? Oh, you can see it. Oh, wonderful, wonderful. So yeah, the question is, which ice hockey player has the most career points in the NHL? This is a simple question in the sense that there's so much information on the internet regarding its answer. So that's why we call it, I say it's a simple question. Now we have picked our threshold, we have inserted our question. Let's see what the tool will be submitted, and let's see what the tool will return. So you see that we get the correct answer. Question is simple, error threshold is high, so the set outputs just one answer. What this means that even with the tool believes that it can satisfy the user's requirement with outputting only one element. Now, let's decrease that error threshold from, for example, 0.8 to something lower, like 0.3. Let's decrease the threshold and note how the number of answers that we get increases. Let's do that. So we decrease the error threshold to around 0.3, and then we insert the same question. Which ice hockey player has the highest point? And see what happens. So now you see that we get not just one answer, but a set of answers that I believe consists of like 4 different answers. The correct answer is still part of the set, but then we also get some other answers that are not correct. But nonetheless, this is not showing occurrence of an error, because error for this application is defined as the output set not containing a correct answer. That is not the case here. But what we just saw here also highlights the difference between two related but different concepts, confidence and accuracy. So in the previous example, when the error threshold was high, the tool, the LLM, gave the correct answer. But the fact that the number of the answers increases so much by decreasing the error threshold indicates that our tool, even though, like the LLM, even though it gave the correct answer, it was not very confident in its outputs. Because if it were confident, then by decreasing this error threshold, it should have given basically the same number of answers. That's not happening, so it's an indication that accuracy, it points the difference between being accurate and being confident. And then, now let's move to the next example, which is going back to what I discussed about elements of reliability. When it comes to LLM, another component of reliability is avoiding hallucination. In other words, if we ask our LLM a question that is particularly difficult, we would like it to abstain from answering, say that I don't know the answer, rather than just hallucinate. And then you will now see how our tool, LLM Religard, allows that to happen. It enables the LLM to know when it doesn't know the answer, and just to simply abstain from answering rather than hallucinate. So we will show that by asking the model a question that is particularly difficult. And it is difficult, I think you can still see the question. The reason I say that this question is difficult is because there is really not that much information about its answer on the internet. The question is, who is the senior vice president of process chemistry at Conformal? So it's very difficult to find the answer for this question on the internet. So now because of that, it's a difficult question. We pick a relatively moderate error threshold. Let's see what the tool will return. See, it returns an empty set. In other words, it doesn't answer. It avoids hallucination. So, yeah. So I hope this example has served its purpose, which was basically motivating and showcasing what conformal predictors can offer to LLM-based applications. In summary, they can offer 2 things. Number 1, they can give the user a sense of uncertainty in the outputs by adapting the length of the output set the user's requirement that reflects their risk tolerance. If they are comfortable with risk, then the tool will include less answers in the output. If they are not comfortable with risk, then the tool will include more and more answers. And then the second thing that it can do is just it helps an LLM to avoid hallucination. When the question is one that the LLM does not know the answer for, then the tool will let the LLM abstain from answering rather than just hallucinate. So now with that, Right. Can we go here? Sorry. Yep. Okay. So yeah, the takeaway message is that I hope you are convinced that conformal predictors have a lot to offer to machine learning and yes, to LLMs. That was the purpose of the previous slide. So any questions so far? Again, please make sure to answer questions because I think as we move on, we will just be, the content will become more and more technical. So it's a good place to just pause and make sure if you have any questions, I'm addressing it. There is a one question. Thank you for the question, Devon. Is the error rate related to frequency of the answer in the output? In other words, if we were to ask the question to this LLM a large number of times, if we were to ask this question a large number of times, the output set would not contain it. I'm not sure I follow the question. Let me read it again. Is the error rate related to frequency of the answer in the output? If we were to ask this question to this LLM a large number of times, the output set would not contain. No, I'm not sure. If I understand your question, the answer is no. In other words, if you keep answering this question from the LLM a large number of times, there's no guarantee that it will contain the correct answer X% of the time. If you do this with a raw LLM, and by raw LLM I mean an LLM that is not equipped with a conformalization layer, there is no guarantee that LLM will be able to do that. So one nice thing about this tool, in general, like about conformal predictors, is that they provide provable statistical guarantees, as I just mentioned earlier. But thank you for the question. If I'm not 100% sure that I understood your question correctly. If that is the case, please feel free to add a follow-up. Otherwise, appreciate it. I will maybe wait for another. Thank you for the follow-up. Sorry, I mean in the conformal structure, trying to understand what the error rate actually represents. Yep, good. Okay, so let me give one other example. Let's go back to maybe our demo here. Just going to be a little difficult to find the appropriate place. Yeah, that's difficult. So let's say that I am a user and the error rate, the error threshold that I insert to the LLM is 40%, is 0.4. What that means is that I want output sets that whose probability of not containing a correct answer is less than 40%. That is what error means in this conformal structure. I think that was. Did that answer your question, David? Okay. Yep. All right. No problem. Thank you for the question. All right. So now we can. So yeah, as I mentioned, the purpose of this example was to hopefully convince you that the conformal predictors really have a lot to offer to LLM applications, and not just LLMs, but basically any LLM application. Now with that, now that we have discussed this motivating example, I want us to take a few steps back and just talk about things that are a little bit more foundational. For example, we discussed what is uncertainty quantification, why it is important. But now the next question is, what are the properties of a good uncertainty quantification method? So it is really sad that I cannot click a particular point here. That is not good. So let's start by a very simple example. Again, here the purpose is to discuss what are the properties of a good uncertainty quantification method. And let's do that by considering a very, I really don't like the way this works. Yeah, oh, right, much better, much better. Yeah, okay, much better. Yeah. So I can see right here, and this will be happier. Yeah, the purpose, I want us to review what are the properties of a good uncertainty quantification. And that is something useful to do because it will allow us to discuss what distinguishes conformal predictors with so many other uncertainty quantification methods. So let's consider, sorry, Jen, I'm now when I switch to this other tab, I don't see the Q&As anymore. I will try to come back to this tab to answer any questions, but if I don't, I would appreciate if you just give me insight. So yeah, let's consider a very simple regression example. This example is really as simple as it gets. We have a collection of points. It consists of x, y pairs. X is our feature, and y is our target value. Now, typically, how it goes is that now that we are given this basically training set, then we fit a model on that training set. The model here in this example, it's a linear model, but it doesn't need to be linear. That's just for the purpose of demonstration. Now, once we fit that model, then the next thing is that we get a new point with, for example, x of equal around 0.5, and then our model makes a prediction for that point. That prediction, because our model is a point predictor, that prediction will be in the form of just one single point. It has no measure. When we do that in our model, our prediction has no idea whatsoever where the true label that is unknown to us may be. It's totally blind the location of that to where that true label will be. Imagine that the true label is represented by the blue circle that is moving around here. Our model has no idea where it may be. It just makes one prediction, the red dot here. Now, what we want to do is that instead of making a point prediction, we want to predict an interval that is centered around our. We want to predict an interval that is centered around the point predictor. We don't want to predict just one value. We want to predict a range of values. And then the other thing that we want to do is we want to be able to connect probabilistic statements to this interval. For example, we want to say that, hey, this is my interval. It covers range from this to that, but then it has it's like 90% prediction interval. What that means is that the probability that it will contain the actual true but unknown label is at least 90%. Because otherwise, if such probabilistic statements cannot be attached to our interval, then they don't have really that much of use. So the first property that a good conformal a good uncertainty quantification method should satisfy is that the probabilistic statements that we attach to it should hold true. In other words, when we say that, for example, we are presenting a 90% prediction interval, then the probability that the interval will contain the true but unknown label should be at least 90%. So this is called coverage validity, and then it's probably the most important property that a good uncertainty quantification method should satisfy. Coverage validity. I want to go back to questions. Are there any questions after this point? No? Okay, so it looks like no questions. I can proceed. And then, but then coverage validity alone is really not enough. Because the other thing that we want to do is that we want our uncertainty quantification method to provide intervals that have valid coverage even when the size of the data set that we have used to construct those intervals is limited. There are methods that can provide intervals with valid coverage only when the size of that data set, the size of the data set used to construct intervals is essentially infinite. It's called asymptotic validity. But that's not very useful, especially in cases where you don't have that much data. So what we really want is an uncertainty quantification method that provides intervals with valid coverage, even when the size of the data set used to construct those intervals is very limited. This is called finite sample validity. Finite sample validity as opposed to asymptotic validity. And then but then even these two are not really enough. We want more things. So we have discussed coverage validity and finite sample validity, but now we want to talk about the third property of a good uncertainty quantification method, and that is related to efficiency. What it means is that if you think about these intervals, you can simply inflate an interval, make it bigger, to make sure that the probability that it will contain the true point is high. But then the price that you pay is that as you make the interval wider, then the interval becomes really not that informative anymore. It just increases the level of uncertainty. So what we want is that we want an uncertainty quantification method that provides intervals with valid coverage that are wide just enough to satisfy a user's requirement, but not wider than that. In other words, we don't want an uncertainty quantification method that will just simply artificially inflate our intervals. We don't want it. This is called efficiency of the intervals. So three properties we have talked about: coverage validity, finite sample coverage validity, and then efficiency. Now, the next thing that we want from our uncertainty quantification method is that is something that satisfies those first three characteristics, regardless of the underlying point predictor. In other words, we want the uncertainty quantification method to be model agnostic. We want to work on any point predictor, be it a simple linear regression, a neural network, or something as complex as an LLM. And we also want it to be distribution free. In other words, we don't want it to be limited to a specific data distribution. We want to satisfy all these nice characteristics that we talked about, regardless of the distribution of the data. So if I summarize it, these are the properties, the characteristics of a good uncertainty quantification method. It should provide finite sample validity, efficiency, it should be model agnostic, and distribution free. So what separates conformal predictors from so many other methods of uncertainty quantification is that conformal predictors have all these four nice characteristics. So that is really what makes them very, very competitive. Now I can go back to the Google Meet. Any questions up to this point? So I will just maybe like pause for a couple of seconds so you guys can make sure that everything is digested. No questions? Yeah, all right. So now we discussed what the properties of a good uncertainty quantification method is. Now we are going to be a little more technical. So before that, what do conformal predictors do? They convert any point predictor into an interval or a set predictor that satisfies those four nice characteristics that we talked about. Finite sample coverage validity, efficiency, being model agnostic, and being distribution free. So yeah, we talked about that. That was kind of a recap. So now we can move to the next step, which is which is discussing some of the really more foundational concepts related to conformal predictors. For example, why are conformal predictors called conformal predictors? What does conformal mean there? That is what we are now going to discuss. So let's go back to our regression example, pair of x, y's. It's a one-dimensional problem, as simple as it gets. We discussed that we fit a model, and then when we get a new point, here represented by this red arrow, we have our model, the true label that is not known to us or to our model. So as far as we are concerned, it can be anywhere in the domain. Now, realizing that, note that if some of these plausible values for the unknown for the test point, and by plausible value, I mean, in this example, any scalar, any value from -infinity to infinity, think of them as plausible values. Some of these plausible values, if we assign it to our test point, some of them will make that test point conform the previous examples. Plausible value, if we assign it to our test point, it will make the test point conform to the previous examples. Where to conform means to comply with expectations. The way you should think about it is that we have a set of points for which we know the label, y here, the white dots on the screen. We have a new point, a test point for which we don't know the label. We have an idea of the plausible values for that unknown label. If we assign some of these plausible values to the test point, then they will make the test point conform to be similar to the points we have observed previously, while some other plausible values will make our point, the test point, really stand out to be very, very different. For example, think about these two red dots that are moving around. If we assign such values to the test point, then our test point will be very non-conforming. It will be very different from other examples that we have seen. So the philosophy behind conformal predictors is that they say the new object for which we don't know the label will have a label that ensures sufficient conformity, sufficient similarity with the previous examples. In other words, conformal predictors do not like test points to stand out, to be different from what we have previously seen. And this is really the very, very foundational concept underpinning all conformal methods. They don't like points to stand up. They assign plausible. They say that the point with an unknown label will have the one that makes it sufficiently conform with the points we have seen previously. Now, with this very, very informal description, we are at the point that we can take the first step towards a more formal definition of conformal predictors. What they say is that they output a set that consists of all plausible labels that if assigned to a new object, and again, new object means an object for which we don't know the label. If assigned to a new object, it will make that object conform sufficiently with the previous objects. So a set of points consists of plausible values that if assigned to a new object will make it sufficiently conform with the previous objects. So now to determine what plausible values will make a new point conform with the previous ones, obviously we need to measure the conformity of point and a bag of points. Or if we want to talk in using more general terms, we can say that we want a function, a metric that measures the conformity of an object with a bag of objects, where a bag is a set that allows repetition. In the previous example, our object was this test point, single test point. Bag of objects were all the other points, the white dots, for which we had the label. So you need a conformal predictors need a function that measures the non-conformity between a point and a bag of points. Now, we need a function like that. What are the possible realizations of such conformity measuring function or non-conformity measuring function? There are different possibilities. One of them, before discussing the possible realizations of such a non-conformity function, let's discuss what properties should a good non-conformity measuring function should satisfy. And for that, let's look into this even simpler regression example. This is really just, it's difficult to imagine an example simpler than this. It's just only for the purpose of illustrating the concepts. So we have a regression with a few points. Some of these points, the blue ones, they fall onto basically the same line. But then we have the two other points, the green and the red one, that are not falling onto that line. In other words, they're kind of standing out, especially the red dot, which is kind of an outlier. So bag of points, some of them really follow the pattern in the bag, but then some of them don't follow the pattern in the bag that much. So a good non-conformity measuring function should be able to acknowledge and measure such differences in the level of conformity that different points exhibit the collection of points. For example, let's consider our bag of all points, and then imagine at a very abstract term, a function that measures, a function f that measures the non-conformity of a point with a bag of points. What that function should be able to do is when it inserts, for example, the red dot here, it should output a high value. It should output a high value for the non-conformity. On the other hand, when it inserts any of these blue dots, it should output a very, very low non-conformity. And in the middle, when it inserts the green dot, it should output an intermediate value for the non-conformity. So in summary, a good non-conformity measuring function should be able to distinguish different levels of non-conformity that different points in the bag will have. What are the possible realizations of such non-conformity measuring function? There are different choices, but one of them, the most basic one, would be absolute errors. What does that mean? It means that when we are given with a bag of all points, what we can do is fit a line through them. It doesn't need to be a line, it can be any model. Just for the purpose of simplicity, let's imagine it's a line, the red line that you see here. Once we have a model like that, then the error encountered by that model for each point can be a measure of the non-conformity of that point with respect to the bag of points. For example, here you see that the red dot, which has been previously discussed, is not conforming to the bag at all, will have a high error. The green dot will have an error that is lower, and the blue ones will have an error that is even lower. So absolute errors are a good candidate for our non-conformity measuring function. Does that mean that the absolute errors are the only candidate? The answer is absolutely not. There are even better choices, but we can just, for the purpose of conveying the concepts, we can just stick with the absolute errors. So I will go back here to make sure that if there are any questions, I'm asked. Any questions? So I can continue. So what have we discussed so far? We have discussed that conformal predictors say output a set that consists of all plausible values that if assigned to new port will make it conform sufficiently with the previous points. And we have introduced absolute errors as one realization of a non-conformity measuring function. Then the next step for us is to discuss how we can use those absolute errors to determine if a plausible label will make a point conform sufficiently with the bag with the previous examples. So we want to use absolute errors to determine if a plausible point will make if a plausible value for the label will make our new test point, for which we don't know the true label, conform sufficiently with the other points for which we have the label. So using absolute errors to determine whether conformity is sufficient or not. Note that this is really a binary determination, meaning that a plausible value will either make a test point conform sufficiently with the previous points or not. It's just a binary decision. But then we cannot make that binary decision using absolute errors only. Why? Because whether a point conforms sufficiently with the other points or not is a relative concept that is influenced by how all the other points in the bag conform to the pattern that existed. To illustrate this, let's go to another simple example. Let's consider this regression problem that has 20 points with labels. They are the blue dots. And let's consider the square as a test point for which we don't know the true label. So all we can do is assign different plausible labels to the square. Here, for example, a plausible label that is assigned to it is just a little above 3. Now, it's very clear, it's very easy to see that with the current plausible value, the square is not conforming the pattern that exists in the back. It's clearly an outlier. But then to demonstrate that this whether it conforms or not is a relative concept, let's do one thing. Let's keep the position of the square the same, but spread all the other points around, spread them away from our line, such that the distance between the square and the line remains almost the same. So we are spreading the other points away from the line, but keeping the distance between the square and the line the same. Now, suddenly, with the same amount, with basically the same amount of absolute error, on the right, you see that the square is starting to conform. This shows that whether a specific value of a plot, a specific value for the absolute error will make a point square here conform sufficiently with the back depends really on the other of non-conforming are all the other points. It's a relative concept. We cannot make that determination using absolute errors only. What can we do instead? We can introduce what I call a conformity ladder. What does that mean? If this is going to be really through, so I would prefer to go back and make sure if there are any questions, I understand. Any questions? I will just pause for a couple of seconds. No questions. So what we can do is we can introduce what I call conformity ladder. What it means is that we have 20 different points, 20 and a square. For each, we have an absolute error that is a measure of its non-conformity. We can sort these non-conformity values from high non-conformity at the bottom to low non-conformity at the top. We sort them and then put them at their ranks. For example, we have 20 different points here. So our conformity ladder will have it. You can think of it as a ladder with 20 different steps. The higher the lower the non-conformity of a point, the higher that point will sit on the ladder. For example, this blue dot here that is pointed to by the arrow will have has the lowest non-conformity, lowest absolute error. So it will sit at the very top of the conformity ladder. The square has an intermediate absolute error, intermediate non-conformity. So it will sit somewhere in the middle of the conformity ladder. And then, for example, this point, I believe, has the highest non-conformity, highest absolute error, highest distance from the yellow line. So it will sit at the bottom. So this is what our non-conformity ladder does. It represents the ranking of different points in the sorted non-conformity array. These ranks are represented by integers from 1 to 20. The lower the non-conformity of a point, the higher it will sit in the ladder. Here we have 20 points, so our ranks will be from 1, 2, 3, all the way up to 20. And then to So these are integers. The ranks are integers, but what we can do is that we can just divide them by the total number of points. So our values are just nicely from 0 to 1. 0 represents very high non-conformity, the bottom of the ladder, and 1 represents a very low non-conformity, the top of the ladder. Now, these are again our vertical axis does not show the non-conformity values themselves, but the rank in the non-conformity array. To have access to the raw non-conformity values, we can add a second axis, a horizontal axis, to our non-conformity ladder that shows the absolute errors themselves. Here you go. So again, this point, low non-conformity, as you can see here by the low value to be read from the horizontal axis. Because of that, a very high rank, top of the ladder. The other point here, very high distance, very high non-conformity, as you can read from the horizontal axis, very low position in the non-conformity array. So I think it's a good place to pause again and make sure if there are any questions, we address them. No questions. So this is, we go through all this, what looks like a complex procedure to decide which plausible values will make the test point here square conform sufficiently with the other points. But we still have to answer one question. What does it mean to conform sufficiently? This ladder allows us to answer that. We can, for example, say that conforming sufficiently means being at the top 90% of the ladder. In other words, if a plausible label will put the square at the top 90%, then that's a value that is resulting in sufficient conformity, thus should be included in our output set. If it's a value that is not putting the square at the top 90%, then we don't need to include it in our predicted set. Now, I will be playing an animation here that contains so much information, so I'm happy to repeat the animation multiple times. But I'm hoping that you guys will be paying close attention to so many things that are going on in the animation. What we have, so the animation will show the square moving around up and down. For each value, as the square moves up and down in the left plot, obviously its position in the conformity ladder that you see on the right will also change. For any value, for any location of the square that results in square being at the top 90%, then you will see this label include. What that means is that we should include that plausible value in our predicted set. And then if it's a plausible value that puts the square outside this top 90%, then the label will change to exclude, meaning that we don't need to put that plausible, we don't need to include that plausible value in our predicted set. So now let's play the animation and please pay attention to all these things that I discussed. Let's see one more time. Further away. Yeah, here it is. So let's start moving the square around. Sorry. 1 second. Yeah, you can maybe here. Yeah, that's a good one. So note that as the square gets closer and closer, the line moves up in the ladder and then comes back down again. I'm gonna play it again. Yeah. Yeah, there we go. So square include was away. Now it turns into exclude, remains exclude until it comes back close enough to be at the top 90% of the ladder. Like moving it back, exclude. Now we go into include and etc. So what this animation is showing is that with the most basic version of conformal predictors, which is called full conformal predictors, what we need to do is to try all different plausible labels for a test point, see which ones make it sufficiently conform with the previous examples, and then collect all those that make that happen, make a test point conform, collect all of them into our predicted set. And then the nice thing about conformal predictors is that once we follow that procedure, then the output set will have a probability of at least 90% of containing actual label. Given a mild assumption about data is satisfied. The assumption is of data exchangeability. You can think of it as a more relaxed version of IID, but going in more detail into what exchangeability means is beyond the scope here. But it's overall, at the very high level, it means that a data set being exchangeable means that the order of the points in the data set does not matter. Think of a spreadsheet containing different rows. If you can shuffle the rows, if it makes sense to shuffle the rows, then your data set is probably exchangeable. The underlying assumption of full conformal predictors are satisfied. You can implement them and benefit from all the advantages that they bring. So this flavor that I showed here is about, oh, sorry, by the way, any questions at this point? Looks like no questions, so we can safely continue. So the animation that I showed where we were moving the square around, moving means experimenting different plausible values. With every new location of the square, we had to fit the model again. Okay, so did not get the difference between IID and exchangeability. A little bit, I'm happy to discuss this, but it's a little bit beyond the scope. But I think you can, any IID sequence is also exchangeable. The other way around may or may not be true. So that's what I mean by exchangeability being a more relaxed assumption than IID. Happy to discuss it more. You can you can definitely reach out to me to discuss this in more detail. We have another question. How can conformal prediction be integrated into time series forecasting to generate reliable uncertainty intervals? Specifically, what practical steps and considerations should be taken to apply this? Great question. Short answer, the time series is not exchangeable. So if you apply the basic flavors of conformal predictors to, like, and when I say basic flavor, like the method that I just showed, to a time series, then because the underlying assumption of exchangeability is violated, the output will not have valid coverage. That being said, this is the question that you asked, conformal prediction with time series. is a very, very active area of research. I'm happy to discuss it in more detail after this event. Feel free to reach out. But the short answer is you cannot apply the most basic flavors of conformal predictors to time series because time series is not exchangeable. Great question. Okay, so any more? Looks like we don't have any further questions. So let's continue. So yeah, with another question, great. What if the previous data are heteroscedastic? Variance increases with X values. No problem. That is not a problem. That is not a problem. They can be heteroscedastic. I'm happy to wait maybe a little more if there are any questions. Otherwise, it will continue. Maybe a couple of more seconds. Okay, so let's continue. Yeah, so what the animation, all we have discussed so far, just represents the most basic version of conformal predictors. They are called full conformal predictors. Now, if you think about it, there's a very obvious problem here. As I move the square around, every time the square moves, every time we want to try a new plausible value, we have to refit the model. So in the animation, if you recall, as the square was moving around, the position of the line was also changing. So if you think of a regression problem where plausible values can be anywhere from -infinity to +infinity, it's obvious that it's just not practical for us to try all these plausible values and refit the model for every of them. It's just computationally prohibitive. So what should we do? You need another flavor of conformal predictors that we are going to discuss now. Let me go to here. This new flavor that does not suffer from that computational problem is called split conformal predictors. I don't believe we have only 10 minutes left, so I don't really believe I have to go. I have the time to go through all the details, so I will just skip directly to the end, which is this. So just like before, where we had this animation representing full conformal predictors on the left, I'm presenting another animation representing split conformal methods. What split conformal methods do is that instead of using all points to measure the non-conformity of the test point, which is what we did with the full conformal methods, we are going to make a split. We are going to split the points for which we have the labels into at least two sets, a training set and so-called calibration set. Training set, we are going to use it to fit our model, the yellow curve here. And then the second part, the calibration set, we are going to use them to measure the non-conformity. In other words, with the full conformal methods, if you look into the conformity ladder, there are 20, we had 20 points, originally 20 points on the ladder. With a split conformal, we are going to split those 20 points into two sets, the solid circles and the empty ones. The empty ones, we are going to use them to fit our model. The solid circles we are not going to use them to fit our model, but we are going to include them in constructing the conformity ladder. Here, I believe I have 10 points for the calibration set. In other words, the split of the labeled data, the training and calibration was half and half. And those 10 points which were not used to fit the model are the only ones that we will include in our conformity ladder. Because of that, and also one other very important point, with the full conformal predictors, the square itself, the test point with a plausible label attached to it, was itself also part of the bag that we use to measure non-conformity. But now with the split conformal, that square is not part of the bag used to measure non-conformities. So because of that, now if we do the same and if we repeat the same animation on the left for full conformal, on the right for split conformal, what you see here is on the right, as we move the square around our model, the yellow curve does not change. Why? Because it's being trained on only the training points, which does not include the square. So because of this, this solves the computational problem of the full conformal predictors. We make a split to training and calibration. We use the training to fit our model, the yellow curve, calibration to measure non-conformities. Because of that, we circumvent the problem of having to refit the model every time the square is being moved around. Let's go back here. Yeah, I think I'm almost running out of time. But overall, so full conformal methods, from full, we go to split, and then, one second. Yeah. So this is, I have to skip a lot of things here, but I think this schematic here shows a good high-level overview of what a split conformal tool does. It inputs a pre-trained point predictor, and when I say pre-trained, meaning that the conformal tool does not care at all about how your model, your point predictor has been trained. It treats it as a black box. The second thing that it inputs is a set of data points that were not used in training the point predictor. That set is called calibration set. And then uses those two inputs and convert the pre-trained point predictor into a reliable interval predictor. And reliable means that the intervals predicted satisfy all those nice properties that we discussed at the beginning of the presentation. So I'm going to wait maybe a couple of seconds if there are any questions. Okay, no questions, so we can move to the next one. So yeah, I think I already did the recap, so I'm going to skip that. But the other nice thing about this split conformal methods is that they are just really, really easy to implement as long as one is aware of a few missteps. If you are aware of those missteps, then the implementation of split conformal is very easy. Why is it easy? Because we can write down a single equation that shows how a point predictor it gets converted into an interval predictor. So, and this slide shows that equation. The equation may seem a little bit intimidating, but if you really think about it, it's a very, very simple one. There is a video on the channel that discusses step by step where this equation is coming from. What we have is y hat representing our point predictor. We have a non-conformity measuring function S. We take the inverse of that non-conformity measuring function. That's what S superscript -1 represents here. And then we insert to that inverse function a specific quantile of the non-conformities. For example, if with the split conformal, if our calibration set has 100 points, we have 100 non-conformity values, we pick a specific quantile from that set of non-conformities, we insert that to the inverse of our non-conformity measuring function. That gives us s minus 1, and then we add and subtract that s minus 1 from the value that we get from our point predictor y. So very easy to implement. And then nice thing is that that interval will have the probability that the interval will contain the true value is higher than the confidence level delta that is given by the user. How high? High just enough to satisfy the requirement, but not higher than that. Mathematically, it means that the probability will have a lower one and an upper one. And then this will hold regardless of the size of the calibration set. If you have, it will, in the videos, I show that even if you have only 4, 5 calibration points, that the inequality, the inequalities will hold. The probability will be higher than what is requested by the user. Now, with that, I just want to very quickly point you to some more advanced applications of conformal predictors in the form of the seminars where I have posted researchers doing nice work on the conformal predictors. Feel free to refer to those videos. One of them that I specifically want to highlight is conformalized retrieval augmented generation. That's, I think, will be very interesting for a lot of attendees here. So yeah, for more advanced applications, please feel free to go there. I don't think I have time to go over the Jupyter notebooks, but you can access those notebooks in the GitHub repository of the channel. If you search GitHub MLBoost, you will be directed there. And again, yeah, of course, you can more than welcome to reach out to me with any questions after this event. That is what I want. Yeah, I think we don't have really time to go any further. But we have 2 minutes left for any questions. If you guys have any otherwise, thanks for being here. I hope it was not too technical. But yeah, again, you're more than welcome to reach out if something was not clear. Any questions? No. All right. MLBoost, yes, MLBoost GitHub. If you got the videos in the description sections of the videos, there's always a link to the notebook that I have used for the material presented in the video. Yep, MLBoost. All right, so time is 2:30. Thank you guys again for being here. I hope you enjoy the rest of the summit. Thank you.